Okay, let's get started. So we're good. Okay. So today we are going to switch gears and start a new topic. So for the past 2 or 3 classes, we talked about communication in distributed systems. We talked about remote procedure calls, remote method invocation. We talked about sockets. We looked at many different systems, including gRPC and so on. Okay, so that is basically the material on communication. Now we are going to switch to things like processes and threads, and we'll build from there, talk about virtualization, cloud computing. So we are basically getting into a different topic. Okay, so today we will start with concurrency in distributed systems. So there are 3 parts to the lecture as usual. I'll talk a little bit about threads. I presume you are at least familiar with it or have some exposure to it either from an undergrad course in operating systems or through any of the projects you have used for your work. But even otherwise, I'll give a quick overview about what threads are, how we use them. Then the bulk of the lecture, the second part, is on concurrency models. So that basically says, how will you design, when you write a client server application, how will you design the server so that it can process multiple client requests coming in at the same time in an efficient manner. Okay, so there are many ways to design these servers, and they all have to do with what kind of concurrency model are you going to use in your server. So that's our part 2. And towards the end, we'll talk a little bit about thread scheduling and some operating system issues that relate to efficiency of threads and so on. Okay, so that's 3 parts to the lecture. Before I start, I also had an announcement. I should have mentioned that earlier. There are multiple assignments out already. Okay, there's a homework 1 that got released on Monday. Okay, earlier today I put homework 2. Okay, homework 2 is not a real homework as the homework mentions. It's basically a tutorial where we have given you sample code for all the work concepts that we learned in the past 2 lectures, RPCs and RMIs and sockets and gRPC. And so we gave you the code already. Your goal is just to read it. They're very short hello world examples, okay, and run it so that you have some familiarity with what these systems do. Okay, so you don't have to write any code in this case. It's just mostly giving you sample code. They're like simple tutorials that you use to get some familiarity. The next lab that is going to come out soon will make you use some of this because you're going to write a client server application. So you better know how some of these concepts work. Okay, so this is just example code to help you with that, right? So take a look at it and make sure you're up to speed on all of these things. Okay, so let's start with threads. Okay, threads and concurrency. Okay, so before we talk about threads, let's talk about a process. Okay, so I presume all of you know what a process is. A process is essentially a program that's executing. Okay, a program is maybe source code that you write or a binary that maybe you generate using a compiler. That's a program. It's a file that sits on disk. When you execute it, it becomes a process. Okay, process is loaded in. So when you have a process, you have program loaded in memory. It has state. That's all of its variables, global, local, stack, heap, and so on. And then it has essentially execution sequence, which is the program counter is executing instructions in that program. Okay, that's essentially our notion of a process. Okay, so there is a single thread of control, which means that there is something executing that program and it's executing one instruction at a time sequential. So we'll call that a flow of control. That's the control flow through the program. Okay, the program has an address space, or rather the process in this case has an address space. That's the memory region allocated to the process by the operating system. Okay, and then it may have some collection of resources, files, semaphores. We don't really worry about that for now. Okay, now take that concept and then let's try to generalize it. Okay, so what is a thread? Okay, a thread is essentially an address space or a traditional process that has multiple concurrent flows of control through them. Okay, So essentially, each flow of control is going to be executing a sequence of instruction, and there are multiple threads that could be part of the same process that execute different instructions of that program concurrently. Okay, I'm going to show you a picture. Okay, all threads are going to share the same address space, but they will have their own stack and own control flow because they could be executing different parts of that program when it's loaded in memory. Okay, and potentially when you have threads, you might need to use synchronization if the threads are accessing shared data structures and so on. Okay, here's a crude picture of this box here is showing you an address space. Okay, that's your program that is loaded in memory, and it's now essentially has a code segment, which is the code. It will have a stack and a heap and so on. Okay, so what you see here, these three boxes are three threads. Okay, each thread has a program counter, its own set of registers and a stack, and then this thread here is executing those in that instruction that is pointing to. Okay, this other thread is executing some other instruction in that address space, and so on. Okay, you can have as many threads as you want, and you essentially get this notion of concurrency, where different parts of the process or the address space are executing different instructions, each by a thread in the program. Okay, that's the concept of a thread that you should keep in mind. Okay, I'm going to pause here for a second to see if there are any questions about a basic concept of a thread. Yes, question.
So you're saying that threads run in synchronous. So like, let's say we have 3 threads running at the same time.
Yeah.
In each of those threads, I go to print out, like just print out any thread A, thread B, thread C. How does the computer choose which thread to print out first? Because they're all being run synchronously.
Okay, so there's a question about when you have a process address space with multiple threads. In this example, 3 threads, they're trying to print something. In what order will the output arrive on the screen? How does the OS decide that? Okay, so first of all, some of this has to do with how the threads themselves get scheduled. Okay, so you have to distinguish. Later on in this class, I will distinguish between concurrency and parallelism. Okay, concurrency essentially means that you can execute different parts of the program, okay, but they don't have to be executing simultaneously. If this multi-threaded process runs on a single core, it's clear that at any time only one thread is actually running, even though there are multiple threads. But you switch between threads. You run a thread for a time slice and you switch to the next thread and so on. But at any time only one thread is running. Okay, but if a multi-threaded program runs on a multi-core machine, you are going to get true parallelism, where 2 threads can simultaneously execute in parallel. Okay, so they're actually executing at the same time. Okay, whereas in the first case, they are time slicing, or you're time multiplexed onto the processor. Okay, so there is that concept. Now, in what order will something get printed depends on in what order the threads actually get scheduled. In reality, if you're running on a single core, the threads are going to be scheduled in some order. Okay, some thread will execute its print instruction first, some other thread next, and so on. That's the order in which you'll see the output. Okay, and there is no guarantee, if you're not going to put synchronization, what order actually there are. You're depending on the OS to run them. Okay, yes, question. Right. So question is this showing 3 threads? So this box is showing the state of each thread. Of course, and that's the program counter that's pointing to instruction. There are registers and so on. Each of them has a stack. I think these gray boxes represent the stack for each of the process, each of the thread. Excuse me. Yes, but there are 3 threads. Yes. Question? Does the process decide how much memory is allocated to each thread? Is that the question? So the memory allocation is done by the operating system, right? The OS decides how much memory to give to the process. Okay, and then the thread runtime decides how much stack to allocate and so on. The heap is shared. Okay, so the memory address space is shared. All of this is shared across the thread, so you can access whatever you want based on functions and global variables if there are any and so on. Okay. Okay. So why would we want to use threads? I already mentioned some of this. If you have larger multiprocessor, multi-core systems, you will get true parallelism. If you had a single threaded process, only that process can only run on one core of the machine. Okay, but you have multiple threads, then that process can divide up its task, and each thread can run in parallel on multiple cores and machine. Okay, now switching between threads of either the same process or even across processes is much more efficient than switching between processes. Okay, the OS has to switch between processes or threads because it has the notion of a time slice where it chooses a thread or a process to run. Okay, and switching between threads happens to be more efficient because they're more lightweight than processes. Okay, and then you're switching between threads of the same process. Okay, that's even cheaper because you don't have to load the process or load its pages. All of that's already there, and you just have to change the program counter, and then basically you can start executing. Okay, so thread operations like thread creation, deletion, switching, etc., are much more efficient and lighter weight than corresponding process operation. Okay, so as a result, having your application, okay, use multiple threads within one address space is often more efficient than having that application be divided up into processes. Okay, remember we are talking about distributed applications, so we are going to eventually put these components across machines. But for now, even the component that runs on one machine, you can partition its functionality across threads or across multiple processes. You don't have to have a single process with one thread running everything. Okay? So this is why I think it's instructive to understand what threads can do for us. Okay, I already said threads have access to the entire address space. Okay, they can access the whole memory of the whatever is in the process. And if you have multiple cores or processes, you will get true parallelism. Even if you don't, you're going to get concurrency. Okay, you have multiple threads executing, but at any time only one thread is actually running. Okay, so here's a very simple example. I don't know if you can see that in the back. This is your traditional process, not a multi-threaded program. It just has a task that prints something, it sleeps for a while, and it's done. So you're basically going to call that function 2 times. Okay, in a single threaded process, each of that is going to execute sequentially one at a time. Okay, so you'll basically execute this, and then you'll execute that. Okay, so here is a time diagram. So you first execute one function. The function has a sleep, as you can see. There'll be some gap, then you'll execute that function again, and so on, and then you'll be done. Okay, that's our sequential execution of a process. Okay, same concept now with threads. Okay, you have the same function. Okay, you want to invoke the function twice, as you saw in the previous example, but in this case, you are going to create 2 threads, and each thread is going to be asked to execute that function or method. Okay, so what is going to happen is the first thread basically starts executing that function. Okay, is going to execute the first statement, and then it goes to sleep, as you can see. Okay, when it does that, if you have a single core machine, you're basically is going to give up the CPU. If you're sleeping, then you don't run on the CPU anymore. So what will happen is at that point, the second thread will start executing. Okay, so you see that task 1 is in the sleep state, but then the second task runs. It also goes to sleep. Then at some point, both of them wake up and it's done. So here you are getting concurrency. Okay, because in the previous case, the first task would have to be completely done. It has to essentially finish its sleep and whatnot before the second task can even run, because it's part of a sequential process. Okay, in this case, you're using multiple threads. Okay, very simple example, but you need to keep this in mind because what we are going to talk about is going to build from this basic concept, which I assume you have some familiarity with. Okay, yes, question. I'm not following the question. Can you repeat your question? Is there a benefit to running what? Say if I was a sequential program for each next line depends on the previous line. Is there any benefit to dividing it on multiple threads, or does it just make sense to run that? Okay, so I didn't fully understand what you're asking, but let me try to paraphrase. This is not talking about clients. It's a single process. Okay, it's just one thread. There's no communication in this. So you're not even gotten to client server programming using threads, okay, which we'll get to shortly. But you're asking if multiple clients are making requests to a server, is there any reason to have multiple threads in that server? Is that your question? Not really. No. So say just an example of this program. Okay. Instead of say putting it on 2 different threads, I have just one large piece of code. Yes. Is there any benefit of Okay, so if your question is if there's a long sequential piece of code, is there any benefit to dividing it up? The answer to that question is if the pieces of that piece of code has independent tasks, you could put them in threads and they will execute concurrently. And if you have multiple processors, they will actually execute in parallel. If they're dependent, if you say I equal to I plus 1 and j equal to I, right, the second one depends on the first instruction having executed. So if you can't parallelize this because there's a dependency. So when you have a piece of code that's dependent, you have to execute them sequentially, or you have to block for whatever you're depending to finish, in which case there's less parallelism or concurrency. Okay, so yes.
As a continuation of this question, if you have shared memory, would that solve the problem of having dependent code be able to run at the same time?
Okay, question is, can shared memory help? Shared memory has nothing to do with concurrency. Okay, shared memory is just a piece of memory that you share between processes, you share between threads and so on. Okay, concurrency is how you execute code. Shared memory is how you share your data.
So I think you kind of answered my question, which was, if I have I equals 1 and then j equals I, if both those variables are stored on shared memory, those two processes could be broken up into threads and run at the same time because they share the same memory.
Okay, so first of all, threads and processes are different concepts. Okay, threads already share the address space. That's about definition. So there is no such thing as having no shared memory. When you have threads, they already share the entire address space. So whatever is in this memory is accessible. So all these global variables will be accessible to all the threads to begin with. So there is no concept of having anything shared. It's already shared. Okay, if you're talking about sharing things across processes, that's a different problem. We are not talking about concurrency using processes. We'll get to that. We are only talking about concurrency using threads. So in threads, assume that whatever is in the address space is already shared. Okay, so that problem is not there to begin with. Okay, yes.
For the next slide, talk about what will happen if that join was before.
Okay, so what will happen if T2 join will be before? Okay, so it's not going to change anything. Join just waits for the thread to finish. It's just waiting for the threads to finish in some order. It has no bearing on in what order they execute. Okay. So you're just two threads, you're waiting for them to finish. It doesn't matter which order they finish, because what matters here is how in what order they execute.
So the print will still be the T1 first print out.
Okay, question is which order will they print? This has nothing to do with join. That's in what order they run, right? So this is just the main program is just waiting for them to finish. Okay, so it will not change anything. Okay, so why do we need threads? What do they give us? I think we mentioned some of this already. So first thing to keep in mind, which is actually has some bearing on what was asked earlier about this long computation, is if you have a single threaded process and it makes any blocking call, it does an IO, it does sleep, it does waits for a lock, any of these things, that entire process will block. It cannot run anymore until whatever it's blocked on is done. The IO is done, it gets a lock, all of those things are done. Okay, so if you have a sequential program and you have any blocking operation and that program is executing as a process, it will block the entire process and the process cannot make any progress. Okay. On the other hand, if you have multiple threads within that process, okay, each thread essentially is a synchronous sequential stream of execution. So if thread 1 makes any blocking call, it blocks on a lock or it does some IO, only that thread will block, but the other threads of that process can continue to execute. So the process as a whole can continue to make some progress. Okay, so single threaded process, when you're blocking calls, there is no progress. In the multi-threaded, you can have blocking system call just as you had in a single threaded process, but because there are independent threads, only that thread that made the call will block. The other threads can continue to execute and make progress. Okay, and there is something in between those two which is called finite state machine or event based concurrency. This basically uses asynchronous IO and events for processing. It allows you to use a single thread, but uses non-blocking operations to emulate what you get with multiple threads in a process. Okay, and I will show you examples of how to do event-based programming as well. Okay, So that lies in between. It has a single threaded process, but tries to emulate the concurrency of a multi-threaded process, okay, without actually using multiple threads. Okay, but from a programming standpoint, threads are much easier to think about because they essentially it's a sequential execution. Each one has synchronous call, so you can reason about your code. You can think about it much more easily than if you had event-based programming where your asynchronous function calls non-blocking. So your process execution essentially jumps from one function to the other because it's asynchronous and you're not allowed to block. Okay, so it's a little harder to debug and think about it. Okay, so we'll get to the pros and cons of multi-threaded versus event-based maybe in a few slides. But let me give you two examples quickly, and then we'll get to actually writing applications, server applications with this concurrency model. Okay? So what can you do with multi-threaded application? So let's take a client, in this case, a web browser. Okay, what would you use the threads for? Okay, if you think about, so first of all modern browsers are multi-threaded. So what would each thread do? So you can take different tasks that a browser performs and hand each one to a thread. Okay, so you can have one thread, say the user clicked on a link, one thread goes fetches the HTML page. Okay, so this one has to make a network connection to the server and download the page. Okay, another thread can essentially parse the page when it came in. Okay, if the page has embedded links, you can have each thread then take one link and fetch it. Maybe there are 7 images. You can have 7 threads fetching those images concurrently rather than fetching them sequentially. Okay, all of this is going to speed up your load time. Otherwise, if you have one thread doing all of this, you have to first get the page, then you have to parse it, then say, let me get image 1. So until image 1 comes, you can't even start the operation to get image 2 because you're doing all of that sequentially. But if you had threads, you could do all of that concurrently. Okay, so while thread 1 is blocked fetching image 1, thread 2 is making a request for image 2 and downloading that in parallel and so on. Okay, so all of that gives you better performance. And then, of course, you can have all these other elements in your page. You may have an ad server, you may have an image server. You can all connect to them in parallel and download things. Okay, so you can write your browser in this case using multiple threads, where each thread is performing some part of the overall application. Okay, and then you basically get better performance because each thread might block, but the browser as a whole continues to run other threads. Okay, that's the client. Now let's talk about servers. Okay, why would you need concurrency in servers? The simplest way to think about this, as shown in the picture here, is a server can listen for client requests. Okay, and the assumption is any number of clients can send a request to the server more or less simultaneously. Okay, so multiple requests are coming in. Okay, if you start processing them sequentially, that's going to slow you down, or slow down the request rather, because the request will just keep queuing up. But on the other hand, if you have threads, okay, within your server, when request 1 comes in, you basically hand it to one thread. Okay, that goes off and processes that request. In the meantime, you can continue to listen for new incoming requests. If another request comes in, you can then hand it to another thread and so on. Okay, so there's this concept of a dispatcher thread that is listening for requests. Okay, and that dispatcher thread takes each request and gives it to a thread saying, go process this. Okay, and each of them can be processed in either concurrently, or if you have multiple cores in your server, you can, of course, process them in parallel. So you are going to get much better throughput, as an example. Okay, as an example advantage. So this is a very simple picture, but it depicts how most servers are written, including web servers that are listening for client requests. Yes, question.
I just want to clarify, when concurrency, does it mean that it only benefits if the process has wait time, or it will be the same as sequential?
The question is what? If concurrency is same as?
Concurrency, for running concurrently, it's only benefiting if the process has wait time, or it will be the same as sequential.
Okay, that I'm still not following your question. So concurrency simply means, in case of multiple threads, that there are multiple threads within the process. Okay, if there's a single core, then you're going to run one thread for a small time slice. Then you're going to switch to another thread. That thread executes some other part of that process. Then you switch to yet another thread, and so on. So essentially, each of the threads is doing some part of that overall application. They all do that concurrently. Okay? If you did this sequentially, then you have to basically do just sequential processing. You have to basically execute function 1, then you can call function 2 and function 3 and so on. Okay, so that's how the two are different.
I think I was thinking about the example before, how like when you ask it, then it has a sleep function. If our process doesn't have sleep, wouldn't that mean that it would be synchronous sequential?
Okay, so you are asking question about how this thread works. So this is something you should actually be familiar with already, but let me still explain why it's different. So you can remove that sleep. It doesn't matter. The sleep is not going to do anything. Okay, because each thread is given a time slice. Okay, so when thread 1 starts, it starts executing task. Okay, maybe when it executes the first instruction, after it executes, the time slice is done. Okay, then the process is going to, the OS is going to switch to another thread. In this case, thread 2 will start running. Okay, and then it will start executing that function. So it's not like just because I removed the sleep, it's not going to be it's going to be same as sequential, because you do have the notion of time slices. Each thread only runs for the time slice that the OS gives it. It's not going to run to completion and then disallow other threads from running. So you are going to switch back and forth between threads. Okay, so it's not the same, even regardless whether the sleep is in there or not. Any other question? Yes. How does the scheduling work? We'll get to thread scheduling. Thread scheduling is no different from process scheduling. Okay, the OS has standard set of schedulers. Again, something, if you've forgotten from your OS, is something you should know, because you have to have some understanding of how this works. But I do have a slide at the very end as to how it is going to work. There is a whole set of scheduling algorithms, okay, that the OS could use, and whatever is actually being done is what the OS will do. Okay, this is separate from, you can actually have within your code, sophisticated applications can choose their own higher application level scheduling. We're not talking about that. We're just talking about if you just run a multi-threaded program, what happens is going to be based on how the OS schedules those threads. Okay, so we are now going to switch from this very simple introduction to threads to concurrency models. Okay, how am I going to write our server application here? Okay, what are various ways to write it? How will we use threads? How can we use other primitives and so on? You have a question? Yes. What's an example of a finite state machine? Finite state machine basically in that case means event-based asynchronous programming. And I'm going to show you an actual example in just a moment. Okay, you need to know something called asynchronous programming for that. Okay, most of the time unless you're writing very high performance applications, you wouldn't want to even touch asynchronous programming. But some very high performance systems actually use it. Okay, they use this event model and so on. And I'm going to give you snippets of examples to explain how that works. Okay. Yes, if you have done Node.js and so on, all of that uses asynchronous programming. JavaScript uses asynchronous programming. Reactive program is very related to asynchronous. So those are basically the same concepts. Your question? Okay. Yes. Okay. Question is which is same question that was asked, but you're asking it slightly differently. If there is a program that has no blocking calls at all, let's say the function is simply a for loop. You do within a function 1 million for operations of a for, and you just add I equal to I plus 1. That's your function. Okay, there's no blocking. Okay. Now you have, so instead of this function here, right, in this task, instead of all this sleep, I just have a for loop that just computes. Okay, so there's no blocking, no sleeping, nothing. And you're asking, is there any difference between sequential and threads, right? And for a single core. And I explained, whatever I explained earlier is still the case. So when you give time to a process to execute on the CPU, it doesn't get time to run to completion. It is going to get what is called a time slice. That's fundamentally how CPU scheduling works. Okay, so you are going to be given a time slice, maybe it's 10 milliseconds. So all that thread can run is for 10 milliseconds. If that for loop doesn't finish in that 10 milliseconds, you will basically pause that thread and the OS is going to switch to something else. In this case, it will switch to thread 2. So thread 2 will start executing that same function. Okay, maybe you only did 100,000 of your million operations. So you will do some part of the for loop of thread 1, then you'll switch to thread 2, do that, come back, and so on. Okay, so you're still getting a difference between sequential and multi-threaded code. Because if it's sequential, you would just execute that entire function. Even though it's not all executing at once, you're time slicing, but there is no other thread to run. When you resume this process, you'll just continue. I'm not sure what you mean by performance will be the same. It's a so in this case, the what is performance is not clear. Okay, so it depends on what you mean by performance. Yes. Is the time taken to complete the task the same? That is a multi-threaded program is not going to change how much time it takes to execute 2 million instructions, 1 million in each function. Okay, because that depends on the speed of the processor. Only thing that the multi-threaded program is doing is interleaving the execution. Instead of executing one and then executing the second, you take the same instructions and you basically interleave them. So they basically, so you will still take the same time. Okay, completion time doesn't change, but lots of other things change. Okay, response times might change and lots of, so those things will change. But yeah, you can't speed up the process because if you're still going to execute the same number of instructions, it's going to take the same time. Okay. Okay, so coming to concurrency model again. So what we are going to do now is to try to understand how to write a server application. Okay, so all of the server applications we are going to talk about essentially are going to follow this model. Okay, they are going to sit in a loop. Okay, within that loop, you are going to wait and listen for a request. Okay, this request is going to come over a network. It can be a socket connection, it can be an RPC, it can be an RMI. It doesn't matter. We are just waiting for a request. The client is going to connect to the server, send a request. How you send a request, that's what we covered in the previous class. Okay, that this class does not worry about that. Okay, so you wait for an incoming request over a network. Okay, and then you are going to process that request. Okay, and you continue in a loop. So you're just sitting, waiting for request, process the request, wait, process the request, and so on. Okay. Now, all of the server models we are going to talk about, the difference in those is how the second step is actually done. Okay. How are you going to process them? Are you going to use threads? Are you going to use events? Are you going to do something else? Okay. So how this step is done will actually give us a variety of different ways of writing that same very basic server, because all servers are going to do exactly the same at the end of the day. They're going to listen to a request and process the request, and they sit in a while loop. Okay. This while loop is called an event loop. The event here is the arrival of a request. So you're basically going to listen for events, which means you'll listen for incoming requests and process them. Okay. So let's start with the first one, which we already kind of saw. That's our sequential server. Okay. So the server code is exactly what we have here. Single threaded process. Okay. No threads. Wait for a request, process the request, then listen for the next request, and so on. Okay. That's also shown in that pseudocode, but it's essentially the same thing. There's no threads anywhere in here. Okay. Simplest possible way to write a server. So advantage, of course, very simple. So disadvantages are if you have a burst of requests arriving, they will all come, they'll queue up at the server. The server is going to take the first one, process. Everything else is still waiting. And there's a second one in process, and so on and so forth. So essentially, all the requests are going to sit in a queue, okay, and wait for their turn. Okay? And essentially, that's going to increase your processing time to process these requests. Okay? So requests will queue up when one request is processed. If you have very low request rate, this is not a problem. If you're going to get one request every 10 minutes and the request takes 1 second to process, this is perfectly fine because you're processing a request. Nothing else is likely to arrive So there's not going to impact the performance. There's no queuing delay because when you arrive, most likely the server is idle. There's nothing there. So you immediately get service. So that's fine. But if you have concurrent or simultaneous arrivals from multiple clients, you are going to see waiting delays, or waiting times will increase and queuing delays will occur. Okay. So how do you deal with this? Okay, we are going to make our server multi-threaded. Okay. So now our event loop is shown in the middle there. Okay. So there are many ways to do multi-threading. Okay. We'll start with the simplest approach. This is called a thread per request model. Okay. As the name suggests, every time a request comes in, you are going to start a new thread. Okay. And you are going to hand that request to the thread, saying, here is a request, go process it. The job of that thread is to process the request. Once it sends back the reply, this thread is going to terminate. Okay. The lifetime of a thread is essentially the lifetime of servicing a request. Okay. So this is called a thread per request model. Okay. Pseudocode is shown here. So you essentially wait for a request. Okay. When the request comes, you create a thread. Okay. You hand the request to that thread and say process. Okay. Now, because this is a thread, it's going to go off to process that request. You can essentially come back and wait for the next request. You don't have to wait for this to finish for you to pull the next request, because threads are executing concurrently. That thread will go off, do something else, and then you can go back and as the master thread, the dispatcher thread, go listen for the next request. So if n requests come, you can pull them one at a time, give them to the thread, but not wait for them to finish to pull the next one. That's the main difference between sequential and concurrent. Okay? Question.
In this model, within the process, each thread, the time to finish the process is longer, because you also have to share the time slice with the other process.
So there is only one process, which is the server process. There are multiple threads within that server process. There is no other process in this case. Okay. There is no finishing time for the process because these are network servers that run. It's like a web server. Web server doesn't finish. Okay. It's just going to run all the time. Okay. So it's just waiting, and as soon as a request comes, it will process it, and then it will wait for the next request and so on and so forth. So it's not like you send it 10 requests and the server is done. That's not this kind of server.
I think what I was wondering is the time to finish each slice becomes longer because you have to share the time slice with other things.
Okay, question is the time to finish a request longer because you have to share the time slice with others? Okay, so that the answer to that question is it depends on what request processing involves. If the request processing is, let me go read a file and send it. Got a request, HTTP request for an HTML file. Request processing often says, go read the file from disk and send it. Okay, so you can send a read request to the disk and you're going to be blocked. The thread cannot actually do anything in the meantime. So you can then process another request, and this is an IO bound operation for a server. If the request is actually doing CPU processing, okay, then you are interleaving multiple requests. So the request processing time for each request will go up a little bit because you are switching, as you rightly asked. Okay, but that's still okay because in the previous case, there's a long waiting time. From the client side, you are going to essentially see how much time it waited and how much processing time it took. So in the sequential case, the wait time is so long that it's better to have very little wait time and slightly high interleaving time than the other way around. Okay? So the overall response time is not just the processing time, but it was also time you waited. Okay? So that is high in the sequential case. Yes, question. Okay, question is how many threads can an application have? Is it limited by the number of cores or CPU? There is no restriction on how many threads can be started. Okay, there are applications that may have thousands of threads. Okay, if they have lots of concurrency, there are applications that may have 10 threads. That is somewhat independent of how many cores you have. Okay, there is an overhead though. Each thread requires you to keep some state. The OS has to keep some state. So there is a small memory overhead that each thread is going to impose. As you have more and more threads, the memory size of that process will grow somewhat. Okay, so in some sense, at the end of the day, you can't have 10 million threads if you don't have enough memory to have the state of those threads. But if you have enough memory, yes, you can even have large numbers of threads. Okay, so it's not limited by definitely not limited by number of cores or anything like that. Okay. Yes, question.
Yes, sir, just in the question, it says maximum number of active threads. Is there an upper limit on the number of active threads that the process can have at any given time?
Okay, there is same question. Is there any limit on the number of threads? There is no limit. In fact, I would encourage you to go and if you have a machine, look at the process table. You can start activity monitor or something equivalent on Windows. Look at a process and you will see by default, like a browser process will have maybe 50 threads. Your mail process will have maybe 50 threads. So most of these multi-threaded applications have dozens of threads, and there is no, and certainly your machine doesn't have dozens of cores. So there is no limit in that sense. Okay. Yes. Yeah, that's coming next. Anything else? Okay. So advantage of this over sequential, newly arriving requests don't wait, because as soon as you hand off your request processing thread, you go back and pull the next request and so on. Okay. So you're essentially assigned to threads for concurrent processing. Disadvantage is that you're creating and deleting lots of threads. Okay. The operation of creating a thread does incur some cost. It may be small, okay, but it's now not zero. Okay. So in this case, the thread is short-lived. So you process the request and the thread is gone. Okay. Then the next request comes, you create yet another thread. So that is wasteful. If you have a high number of requests, you are spending some overhead on thread creation and deletion. That takes away resources that you could have spent for request processing. Okay. So what we'll do is we'll use something called a thread pool. That was the question that was just asked. This is a different model. Okay. In this case, the previous case, you created a thread per request. In this case, we are going to pre-spawn a pool of threads. Okay. When you start the server, look at the pseudocode here. When you start the server, you create n threads. N is a configurable number. Maybe we'll start with n equal to 10. So server starts with 10 threads. Okay. One of these threads is basically going to be doing this listening. Okay, so it's wait for request. Okay, then it's going to pull a request from the when it arrives, and then it's saying, is one of the remaining threads idle in my pool? If so, you hand that request to that thread. That thread goes off and processes that request. So you're not going to create because you already pre-created them. Okay, you just look for an idle thread. Okay, and then you hand it to that thread. Okay, and then you go back, and so on. Okay, so this is going to eliminate the overhead of creating and deleting thread on a per request basis. You create them all at the beginning, and those threads live for the entire duration of the server. Okay, that's an advantage. You are going to get higher efficiency than the previous model. Okay, now what are some disadvantages? Okay, how do you decide what is the right n for your server? Should you pre-spawn 10 threads, 100 threads, 1,000 threads? Okay, how do you decide this? Okay, the answer is it's going to depend on how many concurrent requests are arriving. Okay, n should be roughly equal to how many requests arrive more or less at the same time and are being processed in the system. Okay, and somehow you need to know, either as a developer, well, the developer will just write this as a configurable variable, but whoever is running the server, the IT administrator has to know the workload that is arriving and choose the right n. Okay, what happens if you don't choose the right n? If n is too small, okay, you will essentially have blocking, because what will happen is you'll pull a request and say get an idle thread. All threads are busy because they're still servicing other requests. Okay, this request now has to wait. It's the same problem you had in sequential. There weren't enough. In that case, there's only one thread. So by definition, if the next request arrives, you cannot run. So here, if more than n requests arrive concurrently, the n plus first request has to wait. Okay, and then you have to wait for an idle thread, then you get to run. So it's going to have higher delay. Okay, so if you don't pick the right n, you are going to essentially have blocking for later arriving requests until an idle thread becomes idle. Okay, but if you make the thread pool too large, you're going to waste resources. You can say, let me just create 1,000 threads. Okay, yeah, you could do that, but if you most of the time if you have 2 requests, you have a large number of idle threads just sitting and consuming some memory resources on your system. Okay, that's not good either. Okay, question.
Is there also switching between active threads or active threads?
Okay, question is there any interleaving between idle threads or only active threads switch? So when a thread is idle, it's not doing anything. It's just waiting. Okay, if the thread is waiting, it's not even going to get scheduled for execution. So by definition, there is no execution or interleaving because there's nothing to execute. Okay, only the active threads are the ones that are running on the CPU and getting time slices and switching. Okay. When the idle thread becomes active, it actually has instructions to run. It's doing request processing, so then it will start getting interleaved with other threads. Yes. Yeah. Yeah. So can you change the thread pool, right? That's the next slide. So just wait. So of course, if you want to avoid this problem, you make the tech more sophisticated. We already went from a simple thread per request to a static pool. Okay. If your static pool is a problem, then you essentially want to make the pool dynamic. Okay. So what is a dynamic pool? Basically, you say, I can't figure out a priori what the optimal size is for my thread pool. Okay. The optimal size may change over time. There may be times when there is low load on the server. There may be times when there's high load on the server. When there's high load, you should have a larger thread pool. When there's a low load, you should have a smaller thread pool. So even the right now, n is not going to be fixed over time. It will vary over time. Okay. So what you will do is you are going to essentially start with n threads. Okay. N is any number, and you monitor the number of idle threads in the system. If the number of idle threads falls below a threshold, you say, I need to start more threads because I'm going to run out of threads soon. Okay, so you increase the size of the pool. So there's always some number of idle threads in the system, even though some threads are active. Okay, so this is going to increase n if the number of concurrent requests keeps going up. Okay, and then vice versa is also true. If you made the thread pool very large and the load has dropped and now only small number of threads are active and all of these threads are just sitting there idling, then you can start shrinking the size of the thread pool. Okay, so essentially it needs more sophistication where n is going to be varied. Okay, so I didn't put the pseudo code because in addition to what you had previously, you have to say if the number of idle threads is below a threshold, increase n and start more threads. Okay, and then if the number of idle threads is above some high threshold, okay, then terminate some threads. So there's always some number of idle threads in the system. Okay, so in this case, the pool size is going to vary over time. So this is called a dynamic thread pool. Okay, now many web servers like Apache will use dynamic thread pool. You can also configure what is the number of threads to start, what is the initial n, what's the max. Okay, you don't want if somebody just starts sending requests to cause the denial of service attack. You don't want the number of threads to keep growing arbitrarily because eventually it will crash the system. Okay, so you want to keep an upper limit as well, so that can be configured as a parameter and so on. So you can say the maximum is 10,000. Okay, if you do not want to go above that, I'm just picking a number. That's not anything any real system may ever use, but you can specify that. Okay, so you can say here is the minimum, here is the maximum. You can vary between these minimum and maximum bounds, the size of the thread pool. Okay, that can be specified as well. Okay, so now you don't need to worry about what your optimal n is. You just specify some bounds and let the system do the work. It makes your server more complicated. Okay, because when you are writing the server, you have to write extra code to change the size of the thread pool. Okay, it's no longer just one line where initially you create n threads and you're done. Okay, you will have to basically monitor how many of the n are idle and keep changing that if you need to. Okay, any questions here? Yes. Is there any approach that uses proactive? So this is actually already proactive because you're not waiting for the number of threads to be 0. You're saying if it's below a low threshold, then you increase. Okay? If you wanted to do a reactive approach, you will wait until there are no idle threads. The idle threads become 0, only then you start new thread. That's a purely reactive approach. This one already said I pre-anticipate whether that I'm going to run out of threads and create them, even though I may not use them. Okay, just an estimate that I might need to use. So it is proactive. Other questions? Okay. Next is the asynchronous event loop model. Okay. So this is now going to take us away from threads altogether. We are no longer going to have threads. They are not going to be doing concurrent execution and so on. We are going to start with a single threaded server. Server has only a single thread. Okay. But we cannot do sequential processing because we already know that that's bad for my application's performance because there's a lot of queuing delay. Okay. So we want to emulate what threaded applications or threaded servers do with a single threaded process. Okay. And the way we are going to do this is we are going to use non-blocking operations. Okay. Whenever you're trying to do request processing, but you have to make any blocking calls, you don't block that process. You say, I'm going to let it go do off something and I'm going to switch to something else in the meantime. So you emulate what threads do. Okay. In a threaded application, when a thread blocks, the CPU scheduler in the operating system switches you to another thread. Okay. In an event-based model, when your request makes a blocking call, your code itself will actually switch. You are not depending on the OS to switch to something else. Okay. So that's basically how you're going to emulate concurrency without actually using threads in your application. Okay. This is going to be using something called asynchronous programming. All of your calls have to be non-blocking. If you make a blocking call, your entire process is going to be blocked. There is no switching to anything else because the OS will block you. You cannot run that process anymore. Okay, so inherently you have to write all of your code using non-blocking operations, which means that if it tries to do something that requires actual blocking because the operation is written in a non-blocking way, you basically switch to something else and let that operation continue in the background. So that is basically what we are going to call an asynchronous event loop model. Okay, and here is an example of the synchronous version first, and that's an example of asynchronous version. So here you have a function that's going to basically print 1 and 2, and you call it 3 times. So it's going to execute thrice and just print sequentially. Okay. Here you are essentially going to have the same function, but you have an asynchronous version of that function, which means that when you make any blocking call, which in this case is going to be sleep, okay, you are going to essentially have that thread switch to something else. Okay, so you are now going to call async gather, okay, which we'll ignore that for a moment. You're going to call count 3 times. Okay, just as here you called it 3 times in a for loop, you call count 3 times. Okay, the first time you only have a single thread within this process. Okay, so your main is executing, it's called count, it's going to go here, okay, and then it's going to do that print, and then it's going to essentially go to that sleep. That's blocking. If this was a synchronous, then that entire process would have blocked. But because it's asynchronous and you're using the right things called await, what that will do is it'll come back to this call and say, what else is there to do? Okay, let's just wait for that sleep to happen in the background. So you'll go execute the second count. Okay, you'll go back there, you'll go do the same thing, and then that one is going to block. So you will basically say, I cannot, you are actually not going to block that entire thread, but you are going to come back here and then continue and so on. Okay. So your code is the one that's actually switching back and forth instead of the OS switching between threads, okay, and achieving the same concurrency as a result. But this makes code a little more complicated to write because you are writing this as a programmer, but it's giving you the same benefits overall. Yes. Okay, question is, what will this print? Will it print 1, 1, 1, 2, 2, 2? Okay, if that sleep is long enough, okay, you will essentially print 3 ones because now all the counts are finished. Okay, then the first sleep will expire. Then you will go back and finish the next statement there. And then you will print 2, and then you will basically go to the other count and so on. Okay, that's how it should actually be here. Yes. Okay, question is, what does it mean to be handled in the background? Right? Normally, if you call sleep within any code, okay, you basically sleep. You basically put that thread to sleep. It doesn't do anything until the sleep period expires, then you continue execution. That's what sleep, that is called synchronous sleep. That's normal sleep. Okay. But this is what an asynchronous sleep. That basically means that you still want this function that's executing to sleep, but you don't want the code as a whole to stop executing. So you will essentially have that function execution block. Okay, so it's basically now sleeping, but you try to execute something else in your actual thread. So here you'll come back and execute another version of that count, or you could have executed something else. Okay, so when that sleep actually finishes, you're done with 1 second, then you can go back and continue execution at some point, right? So you may switch back and so on. If there are 100 of these, maybe you will do 4 and then that sleep for the first one will expire, then you might go back there. How you switch also depends based on the event. Okay, but that is what is going to happen effectively. Yes, question. Yeah, so how does the question is, how will this know what all things are there to execute when the blocking call gets done and so on, right? So typically the asynchronous, that's how you will implement this asynchronous blocking, sorry, asynchronous non-blocking. Okay, and typically if you're doing asynchronous IO, let's say a simple example is you try to read a file from disk. Okay? Standard read is blocking. If you say read, you are waiting for the disk to actually retrieve that file and give it to you, then the read returns. Right? If you use asynchronous read, you will basically send that read request to the OS. Okay, but the read will, that function will return immediately. Okay, and then you will basically continue execution in your process. Okay? When that read actually finishes, the OS will then send a signal to the process saying your read is completed. So that will appear as another event. Okay, so then you have to basically go back to whatever had issued that asynchronous call and then continue execution from that. So there is some switching that has to happen. There are notifications that will come and so on. Yes, so essentially there's a thread and there is an event queue, which is basically all these asynchronous events, which you don't see in the code, but internally that's how you're going to implement them. So you're pulling events of the event queue and say, what do I do with this? Okay, so in this case, if that sleep is done, then you continue executing whatever had sort of issued that sleep and so on. Okay, any questions on this? Yes. Yes, the question is, asynchronous model, it looks like sequential code, but the code can execute different parts. That's exactly what's happening here. Essentially, you may have to switch back and forth between these counts and so on, okay, based on when this blocks, and then it yields the control back saying, okay, now I'm go back to whatever you were executing before and so on and so forth, right? So you have a single thread that is switching back and forth different parts of your code. Okay, now in multi-threaded, you have different threads that are essentially executing different parts. The OS is switching between them. Okay, here there's one thread that's just switching across different parts of it. So that's the difference. But in the end, you're getting concurrency in either case. Okay. That's asynchronous event model. Here's an asynchronous event loop. Okay, this is actual Python code. Okay, this is how you will write a hello world server. Okay, in Python, essentially you have to call the async IO package, and then the event loop is actually implemented by the Python runtime. So you essentially have to call a get event loop, and that constructs an event loop for you. Okay, and then you essentially, for that loop, you can call many asynchronous functions, as many as you want. Here we just call one hello world is going to execute that hello world. Okay, but in general, within that event loop, you can call other functions and so on. Okay, so it's just going to sit in a loop, wait for events to actually occur. Okay. Here's another version of it where you essentially have, so in this case, that hello world was actually not asynchronous, as you can see. Okay, so when this event loop calls that block of code is executing continuously. Okay, but whatever the event loop calls itself can be asynchronous. So, and you do that by using the async keyword before a function. Okay, so instead of just using def and having hello world, you say there's async def. Okay, that says that function itself can be asynchronous. So while it is executing, you can switch out of that function and do something else. Okay? If you don't have an async and you enter a function, you will have to actually execute it. Okay? So if you make a function async, all the blocking calls in there, if you have any, should be also made async. Otherwise, you will have blocking in there. So that essentially there is another keyword called await, asynchronous wait, that always essentially is paired with async. Okay? So you can essentially make a function async, and if it has any blocking call, you can say await and do that. So that way it will not block it. It will go off, do that, and do something else. Okay? So this is just a very quick overview of how Python does it. Of course, different languages will have different ways of writing it, but the concept is very similar. Okay, of how you do this. There are many languages that are fundamentally asynchronous. Node.js, JavaScript, that basically use event-based model. Okay, but other languages like Python and Java, they're by default synchronous, and even C, C++. But they also provide packages that allow you to write asynchronous code. Okay, as opposed to others that are by default asynchronous. Yes, question.
Is the left one multiple from the one and the right one only once, or is it both of them only once?
Okay, the question is, so the left one is only going to call the hello world one. This is just showing how to make an event loop. But if the function is not asynchronous, the event loop is just going to execute that. It's not going to be able to switch to anything else. Okay, in this case, you have an event loop, and then you call hello world, but you can essentially switch to something else. Now you are asking, will it execute multiple times? In this case, it's not executing multiple times, but you can call it again if you want. Yeah. Okay, any other question? Okay, this is just a simple example. And then again, we'll give you some sample code that you can run and try this and try to understand better, because there's no better way than actually looking at code and trying it out. Even better ways to write your own code, but that you can wait for until the lab comes. Okay. All right. That is our event loop model. There's one more model I want to mention, then we'll try to summarize them. This is the process pool model. Okay. So far, we only looked at a single process, and we said either there can be multiple threads within that process, or there can be a single thread that can do event-based asynchronous processing. Okay. But you can have a server that actually has multiple processes. Each process can do some part of that overall application. So you can say this application has 5 processes. This first process is responsible for this task. Second process is responsible for some other task, and so on and so forth. Okay. So you can write your application as a multiple server process. Okay. You can also write our network server application as a process pool. Okay. So instead of creating a set of threads, you can have a request per process model, where a request comes in. Instead of creating a thread, you create a process and you hand the request to that process. Okay, it'll go off and execute that process, that request. Okay. Okay, the overhead of creating a process is going to be much, much higher than creating threads. So a request per process model is going to be even more expensive than a request per thread model. Okay. And of course, you can create a process pool. You can have a dynamic process pool, just as your thread pool. Okay. So you can pre-spawn a set of processes. Request comes in, you hand it to a process. Okay. This is, of course, going to require inter-process communication, because one process has to then hand the request to another process, and so on and so forth. But the concepts are similar. Okay. So you're basically using process as the granularity of concurrency, rather than using threads as your granularity of concurrency. Okay. So you can say, what are some advantages and disadvantages of this? Okay. The one advantage of a process-based model for the servers is, if a process crashes, the other process continues to run. Okay, because each process is independent. Okay, if your browser crashes on your machine, other things are still running, because that's a single process. That's the only thing that got impacted by it. Okay. But when you have multi-threaded server, okay, all threads are part of the same process. So one thread has a bug in it and it crashes, the entire process is gone. The server itself comes down or goes down, right? So this has a little more resilient property than having a threaded, especially if you have bugs and things of that sort. Okay. So workers process crashes only impacts that request, but not the application. Okay. The second advantage is there's address space isolation. Okay. If you have threads, since one thread can see the entire address space, okay, if you have threads, they can actually see what other threads are doing. If you're doing something sensitive within your server, if you have them separated out as processes, one process doesn't have access to another process's memory. Okay, because the address space is limiting you to what you can see to your own address space. Okay, so that's another advantage. Okay, disadvantage is, of course, this is going to be more expensive because process switching is more heavyweight than thread switching. Okay, now there are examples of where this model is used. Okay, earlier versions of Apache and even now, okay, Apache by default uses a process pool model. It can also do multi-threading, but the default has always been you create n processes. Okay, and the process, the pool size is very dynamic. It's a dynamic process pool. Okay, similar to how we looked at dynamic thread pool. Okay, even browsers actually use this. Okay, so Chrome actually starts each tab that you create in a separate process. So you have address space isolation. So that way, if you have some malicious code that you have in one tab, it cannot actually look at what another tab is doing. So if you're doing online banking in one tab and something else is running that downloads some malicious code, the tabs you cannot actually peek into someone else's address space. Okay, so it gives you more resilience. And if one tab crashes, your browser still stays up. Okay, if you have some buggy JavaScript or something like that. Okay, as opposed to if you have just a multi-threaded browser, there's bad code, it will just crash your browser or hang. Your browser will hang. Okay, so many applications will use this for a variety of reasons, even though it comes at a higher cost. Questions on this? Okay. So very quickly, we'll just compare them. Okay, so you have sequential. Okay, so you can do one request at a time. Okay, which is not what you want to do. But if you're sequential architectures, then you want to essentially do asynchronous programming and get some concurrency. Okay, and then you have concurrent, which could be thread-based concurrency or process-based concurrency. Okay, and we can use either one and get the benefits of concurrency. Okay. So essentially, the four models are pure sequential, event-based, multi-threaded or thread-based, and process-based. Okay, and there's a question at the bottom saying which one is most efficient. The question should be what, or should be in what regard? What does efficiency mean? Okay, so in this case, it could just mean in terms of the overheads of the architecture. Okay, so it's a switching cost, right? So thread-based will have lower switching costs than process-based because switching between threads is cheaper than this. Okay, pure sequential just doesn't have good performance. Okay, so then there's a question of event-based versus thread-based. Which one has higher efficiency? Maybe I can ask for suggestions on what you think. From an overhead and efficiency perspective, is event-based higher overhead or lower overhead than a multi-threaded architecture? No, multi-process is process-based. Okay, multi-thread is single process, n threads. That's just one process. That's n processes. No, process-based will have the highest switching costs because it's switching between processes. Okay, so it will have, from efficiency standpoint, least efficiency. Yes. Can event-based be multi-threaded? It can be multi-threaded. I'll get to that. But right now, we're just saying a single thread. Okay? So it turns out this single thread event-based has the highest efficiency because there's no switching between threads. Okay? In the multi-threaded case, you're at least switching between threads of a process. In the event-based, there's only one thread between the process. So if I switch from one part of my code to another, okay, I don't actually need to switch threads to do that. Okay, basically my same thread is jumping from one part of the code to the other. So that is going to be the highest efficiency. Okay, so very high performance servers for that reason are essentially written using an event-based architecture. Okay, because it gives you the highest efficiency and performance. Okay, having said that, it's the hardest to write because the code is actually much harder to write from a programming standpoint than threading based. Okay, and then there's another way to compare this, which is concurrency and parallelism. Okay, concurrency, I said, essentially enables you to handle multiple tasks within a process, multiple requests, and so on. Okay, and one processing of one does not block the others, even though it may block itself. Okay, parallelism is achieved when you have true simultaneous processing. So for parallelism, you need multiple cores. For concurrency, you need one core, but either you do event-based or multi-threading. Okay, you still get concurrency, but in that case, only one entity is actually executing on the processor. Okay, now, as far as the event-based architecture is concerned, if you say what is your efficiency when you have multiple cores, okay, multi-threading will win because multiple threads can actually run on multiple cores. In event-based, there's only one thread, so it can, even if you have 10 cores, it will only run on one. Okay, so even though it's more efficient on a single core, when you have multiple cores, you will not get the benefit of true parallelism. Okay? For that reason, you can actually write event-based architecture with multiple threads. That was such a question that was asked, where if you have n cores, you should have n event loops in parallel, one running on each core, and each of them does asynchronous processing. Okay? Then you will get the best of both worlds, where there's one thread per core, and then each of that thread is actually doing event processing. Okay, that's a hybrid architecture, is even more complicated than simply writing event-based programming, but that's what you have to do if you want to get really high performance. Okay, yes, question.
Would you consider having a hybrid of thread-based and process-based?
Okay. Yeah. So question is, can you have thread-based and process-based? You can, of course, do that. You can have multiple threads within a process. You hand a request, and the request processing can be split across multiple threads and so on. So that is also common. Yeah, so any combination you can think of, somebody has looked at. Okay, so we have only a couple minutes, so I'm going to start this and we'll continue next time. So the last part was trying to get some understanding of how thread scheduling works. Okay, so this is again a little bit of a recap of some concepts that you probably encountered in an undergrad class, but I'm going to talk about them here. Okay, so we talked a lot about threads and concurrency. It's instructive to understand how they're implemented and how the OS deals with them. Okay, so there are two types of thread implementations. One is called user level threads. The other is called kernel level threads. Okay, user level threads essentially says that the abstraction of a thread is implemented in a user level library. It doesn't use any OS support at all. The whole concept of a thread is essentially something that you implement in some libraries. Okay, and applications can create threads, delete threads, all of that is still the case. Okay, but all of the thread management is done by your library. It's not done by the OS. Okay, so the OS sees that entire process as having a single thread because it doesn't know that there are real threads in it, because threads are being managed at an application level inside a library. So OS perceives this entire address space as having a single thread, even though there are multiple threads in that process. Okay, now user level threads are very efficient because all of the thread management is simply a library call. It's not a system call to the OS because the OS is not involved. Okay, so switching between threads is also efficient. It's a library call and so on. Okay, disadvantage is you cannot take advantage of true parallelism. Even though there may be 100 user level threads in your process, the OS sees it as a single process, single threaded process. It doesn't know there are all these threads. So it cannot run this process on multiple cores or multiple processors. Okay, here's an example, a picture. So here, each of these boxes is a process. There's a library and there's a library scheduler. These arrows, circular arrows are threads. So this one has 2 threads, 3 threads, 3 threads, and each of them essentially is running. From the OS's perspective, it looks like these are all single threaded processes. There are 2 cores, so it's pick those 2 and run them here. Okay? You can never run 2 of these threads in parallel, but you can run 2 different processes in parallel, but not threads within the same process in parallel. Okay? That's a disadvantage. And I'm going to just quickly show kernel level thread picture. We'll come back to this next time. So here in kernel level threads, the kernel is actually not only aware, but managing threads for the process. So to create a thread, you have to tell the OS, create another thread within this process. Okay, to delete a thread, you have to tell the OS, delete a thread from this process. So the OS knows about threads, it can see the presence of threads and so on. So you see that all of this is the OS. This OS can see all of the threads and explicitly pick threads to schedule. So in particular, you can pick 2 threads from the same process and put them on the 2 different cores, and you will get true parallelism, okay, which you could not get earlier. Okay, but the disadvantage is now thread management is now something that the OS has to handle for you. The OS has to support threads and so on. Just quick question.
Implementing that library threads, is it as simple as just having a dynamic list that you append processes, or not processes in this term, but like you're running certain
Right.
aspects, you put that in the list and then just the list runs through each clock cycle?
Right. So how do you write a user level threads library? Typically, the user level threads library itself has to use event-based programming. Okay, it has to look at the threads as being blocks of code, and switching it is basically saying that I ran this, then I'm going to switch to some other threads and run something else and so on. But you still have to provide the same APIs that you provide to any other thread. So your interface has not changed. You could use JVM or Java threads, okay, and you implement them as user level threads. So you still have to do all of that work of providing that abstraction, but you do that in the library as opposed to doing that in the OS. Okay, so we'll come back to this next time. We ran over time, so let's stop here today. Okay.